Hi everyone, we're looking at momentum today, so find chapter 6 in your notes. We start off with the definition of momentum. So the momentum of an object is the product of its mass and velocity. So the letter for momentum is P, and then we have our usual mass and velocity M and V there. The reason why P stands for momentum is basically because otherwise it'd be confused with mass if we used M, and German scientists decided back in the day that P would be the letter for it, and it's kind of stuck. So, just reading through the notes here, we have more loosely, momentum is a measure of how much effort it would take to stop the moving object. And you may be familiar with momentum from a sporting sense. that was the first place I ever heard of it. A team might have momentum and they might be scoring a lot of goals or something, and it just means that it's harder for the other team to stop them once they get a run on. Anyway, momentum is a measure of how much effort it will take to stop the moving object. So if we have more momentum, we expect something to be harder to stop than something that had less momentum. So another point here is momentum is a vector, so it has both magnitude and direction, and have to remember this when answering exam problems. Okay, so we'll have a look at the introductory exercises here. So what is the momentum of a truck of mass 5 tons travelling west at speed of 20 kilometers per hour? And if you look back up to your notes and you look next to mass, it's in units of kilograms, and velocity is meters per second. Okay, so if you're unaware, tons is equal to 1,000, so this truck will have a mass of 5,000, so let's put that into our equation. So P equals mv. We have 5,000 for our kilograms. 20 kilometers per hour, so we want that in meters per second. And if you're starting with kilometers per hour and you want to go to meters per second, we need to divide by 3.6. So we have 20 divided by 3.6. Okay, and then when we put that into our calculator, we should get 27,077, and we can round the next one up to 8. That's in kilograms meters per second, but I'm going to take it to 3 significant figures. So it's 27,800 kilograms meters per second. And just note the direction is west, so we have to put that in west. And we can just put here 3 significant figures there, just to note that we've gone to 3 significant figures. Okay, a flight of mass, so we're going to question B now. So a flight of mass 2 grams, travelling with a speed of 10 meters per second due north. Okay, so if we can put that straight into our equation as well, but remember the mass has to be in kilograms, so if we're given grams we have to divide that by 1,000, so you can write it that way, and 10 meters a second is already meters a second, so we can write 10 down here. Now the other way of writing 2 divided by 1,000, we can write it as 2 times 10 to the negative 3 times by 10. It's quite convenient in this case because now, because it's 10 meters a second, we can see that's equal to 2 times 10 to the negative 2, which is equal to 0.02 kilograms meters per second. And that one is, what is it? North. Okay, so we're in north. Okay, just ignore that email, guys. Thanks. Thank you, Jason. Okay, so an electron of mass 9.1 times 10 to the negative 31, travelling south with a speed of 10 to the power of 8 meters per second. Okay, so we can put these straight in because they're in, this should be in kilograms. A mass of 9.1 times 10 to the negative 31, that's actually kilograms. So you can put that straight in, 9.1 times 10 to the negative 31 times by 10 to the 8. So our inner C laws, because these tens are times together, we add those numbers, so it's 9.1 times 10 to the negative 23 kilograms meters per second, and it is travelling south. Alrighty, so that's the first introductory exercises. We now have a look at a truck of mass 4 tons travelling north with a speed of 100 kilometers per hour and a car travelling west at a speed of 60 kilometers per hour, and they constitute a closed system. Okay, so I'll just quickly talk about a closed system. This might be a bit of a new concept, but if we have a closed system, it means that we can essentially just draw or pretend these two objects are in a box, and what we know is that the momentum within that system is that it'll be conserved. So when we talk about conservation of momentum, this will make more sense, but we just want to kind of start to think about objects being within a system, and they may or may not interact with each other. But as long as those two things are the only two things within this system, then the momentum will be conserved. Okay? But we can just do some maths on it. So we have a track of mass 4 tons. So let's do the truck. So let's say P of truck is equal to 4 tons, so 4,000. That's our mass. With a speed of 100 kilometers per hour. So again, changing it to meters a second, starting with kilometers per hour, which is divided by 3.6. That comes out as 111,111 kilograms meters per second. So I'm going to put that again to 3 significant figures. Okay, I'm going to do it in scientific notation this time. So it's 111 times 10 to the 3 kilograms meters per second. And it is travelling, where is it travelling? North. So it's travelling north. Okay. 111 times 10 to the 3 kilograms meters per second north. Momentum of the car is next, so we have momentum of the car is equal to 800 kilograms times by 60 divided by 3.6. And that comes out as 13.3 times 10 to the 3 kilograms meters per second. And that one is west. Okay, and again, I've just gone to 3 significant figures for both of those. So now it asks for the total momentum of the system, which is essentially, we can think of this as just 2 vectors. So we have a vector going north and a vector going west. Okay, you've done vector calculations before, so we want to firstly do a vector diagram. So, oops, struggling to get. I'll just try and do a straight. Let's see if I can do a straight line. There we go. No, it's okay. So this one's 111 times 10 to the 3 kilograms meters per second. And then we have another one going west. And this one here was 13.3 times 10 to the 3. And then our resultant vector goes between those two, and we have an angle in here, theta. Okay, I'm going to call this P of the system. So P of the system, and that's what we want to find out, and we need to find out the direction of this system as well. So it's just, because this is a little right angle triangle in here, we can do P of the system. No, not there. Press the button. Oh well. P of the system is equal to square root of 111 squared times by 13.3 squared. And you can go through the maths if you like, but basically because they're both times 10 to the power of 3, we can just put a times 10 to the power of 3 out there. And if you feel like a little challenge, you can go through the maths of that to prove that I'm right. Okay, and then when we do the square root of that, we go 100, it comes out as 112 times 10 to the 3, 10 to the 3 kilograms meters per second. Now we need to work out what the angle is, so that theta is equal to the inverse tan function of 13.3 over 111. Okay, you can put in times 10 to the 3 inside the brackets as well, but they're just going to cancel out because you're dividing one by the other. Oops, I don't know what's happened. Oh, it's not responding. Let's see if it's going to respond to us. 13.3. What's happening? Let's see, I'll just pause this video.